Thank you very much, Mr. Chancellor. My name is Martha Piper, and I am the Interim President and Vice Chancellor of the University of British Columbia. Every year at Congregation, UBC has the honor of bestowing honorary degrees upon individuals who, in the opinion of the university community, have fit the criteria of excellence and eminence in their chosen field. Susan Solomon is one of those individuals, and I invite her to step forward now to receive her honorary degree. Mr. Chancellor, Susan Solomon is the Ellen Swallow Richards Professor of Atmospheric Chemistry and Climate Science at the Massachusetts Institute of Technology, MIT, and is widely recognized as a global leader in the field of atmospheric science. She and her colleagues have made important contributions to understanding chemistry and climate coupling, including critically important research findings on the irreversibility of global warming linked to anthropogenic carbon dioxide emissions. After receiving her doctorate in atmospheric chemistry from the University of California, Berkeley, Dr. Solomon embarked on a long and remarkable research career at the National Oceanic and Atmospheric Administration, where in 1986 she proposed that refrigerants and other industrial chemicals were responsible for the Antarctic ozone hole discovered a year earlier. Later that same year, she began work as the head project scientist of the National Ozone Expedition at McMurdo Station, Antarctica, where she and her team collected some of the earliest data linking chlorofluorocarbons to the deterioration of the ozone layer. She also showed that volcanoes could accelerate the reactions caused by chlorofluorocarbons and therefore increase the damage to the ozone layer. Her work subsequently formed the basis of the UN Montreal Protocol, an international agreement to protect the ozone layer by regulating damaging chemicals. She has also worked as a member of the Intergovernmental Panel on Climate Change, which along with Al Gore was a co-recipient of the 2007 Nobel Peace Prize. Her many other awards include the National Medal of Science and the prestigious Vetlesen Prize, which recognizes globally significant achievement in earth sciences. She is a member of the U.S. National Academy of Sciences, the European Academy of Sciences, and the French Academy of Sciences. Mr. Chancellor, on behalf of a university dedicated to research excellence and sustainability, and in recognition of her extraordinary and critical contributions to climate change research, I ask you to confer the degree Doctor of Science honoris causa upon Susan Solomon.
By the authority of the Senate of this university, I confer upon you, Susan Solomon, the title and degree Doctor of Science honoris causa.
It now gives me great pleasure to call upon Dr. Solomon to say a few words.
Thank you so much. What a lovely presentation that was, and how great it is to be in this wonderful institution and share this remarkable ceremony with you. I thought that the best way to thank all of you would be to think carefully about what to say today and try to make it something that would give you a little bit of food for thought. I've been very, very lucky in my life. I've applied chemistry to one of the most spectacular environmental challenges that's been observed so far on this planet, the Antarctic ozone hole. It was discovered almost 30 years ago now by a small and little-known group of people working at the British Antarctic Survey, and it was a tremendous shock to the world when they announced that they had measured this gaping hole in the ozone layer. I feel truly privileged that I had the chance to do research on the ozone hole following that pioneering discovery. Plus, I got to go to Antarctica, which is one of the most amazing experiences that anyone could have. So it's a crystalline, wonderful place to be, like your own Arctic, and it's just an amazing experience for a scientist. It was the kind of thing that could happen only to someone who really had a great fortune happen to them. And within a few years, the Montreal Protocol was established. So today on this planet, there are no more emissions of the compounds that are damaging our ozone layer. We solved this problem. It'll take many years for the ozone hole to close because these molecules have very long lifetimes. And so we'll live with the legacy of that for quite a few decades. But we have indeed solved this planetary challenge. And today we have an even bigger planetary challenge. It's climate change. Its main cause is the carbon dioxide that we put into our atmosphere by burning fossil fuels mainly when we drive around in our cars or when power plants use coal or to a lesser extent natural gas. And it's remarkable. You can go to Antarctica and dig up an ice core, and the ice cores have little bubbles in them, saving air that goes back 800,000 years. Almost 1 million years of Earth's history in ice cores are available. And what you find is that human activities have increased carbon dioxide by about 1/3 since the Industrial Revolution began. So we have something like 35% more carbon dioxide in the atmosphere today than there's been in 1 million years at least. So to lighten the atmosphere a little, the bad news for the young people today is that they're inheriting a dangerously changed planet. And the good news is it's a problem they can blame on their parents and grandparents. But seriously, let's talk about what to do next. It's very much a problem of risk. We know we've increased the amount of carbon dioxide on this planet. It's a strong greenhouse gas that traps heat, and we know the planet is getting hotter. One of the clearest signs of global warming is that we're setting more and more record daily hot temperatures all around the planet. And importantly, we're setting very, very few cold records. So that tells us clearly that the temperature of our planet is shifting. It's also causing increases in global heat waves, which can lead to fatalities. So climate change is about risk. We know a great deal. There's a lot we don't know, especially about the impacts of a warmer planet on animals, plants, ecosystems, and, of course, human society. So how much risk we're willing to accept is the issue we're grappling with, and that's a question of values and not of science. I want to take just a few more minutes to talk about another aspect of values in climate change. On Monday, the nations of the world, as you probably know, are going to gather in Paris to try to finalize a United Nations agreement on what to do about climate change. It's going to be a historic couple of weeks. It's important to ask how much carbon dioxide different people around the world are contributing to the problem. And in the U.S., the average person emits about 17 tons of carbon dioxide per year, and your number here in Canada is quite close to that. We emit in North America about twice as much as the average European. But the more important point to consider is how we and the Europeans live compared to how the world's poor live. We emit about 10 times more carbon per person per year than the average person in India, about 50 times more than the average Kenyan, and about 170 times more than the average Ethiopian. So that means that in a year, every one of us emits as much as a typical Ethiopian village does, because a typical village has about 150 to 200 people in Ethiopia. There's about 1 billion people in the developed world today and about 6 billion in the developing world. If you average across the whole planet, the average person in the developed world today emits about 4 times more carbon dioxide per person in a year than the average person in the developing world. So we're embarking on a wonderful century. Poor people all around the world are developing. They want to enjoy a higher standard of living than was ever possible before, and we all understand that the need for development to continue on a path that will provide people with better housing, food, abundant water, health care, all of that takes energy, and most of the world's energy today comes from fossil fuels, which means carbon dioxide emission. So we as a world are facing some critical choices. How we decide how much carbon to emit in a world where all of us, not just in the developed world, but all of us want to, and in my opinion, should live better. Well, please don't be discouraged. One of the great pleasures that I have at MIT is teaching students about the history of environmental challenges that the world has faced in the past. And it's remarkable how we've dealt with a whole string of issues, one after another, getting lead out of paint and gasoline, safeguarding our children from smog, cleaning up acid rain, and of course the ozone hole, the signature example where we made some very smart choices as a world. Climate change is indeed a very big issue, bigger than any of those. But in every one of those past challenges, public engagement, public opinion really mattered, and advances in science and technology were key. Progress happened very fast when we took an approach that spanned science and solutions. So I think when you look back at all those successes, it can't help but give you a lot of hope about what is going to happen next. I'm a tremendous optimist about this. I think people are curious and inventive about this problem. They can be turned on to the search for solutions. Here in British Columbia, you've done some amazing things. There's not much time to waste, but the train of understanding has definitely left the station, and we're going to see where it goes beginning Monday morning in Paris. I think it's going to be on an unstoppable journey of arriving at a better planet for all of us. Thank you for your attention.
Thank you very much, Dr. Solomon. Thank you for accepting our degree and becoming part of our UBC family. And thank you for being such an extraordinary role model for our students and our graduates who, through your actions, have shown that applying science rigorously, appropriately, and in an excellent way can truly, an individual scientist can truly have an impact on a worldwide problem. So thank you very much.